Good evening. Welcome to the Honest Investigators Talk Shop Show. I'm your host, Doug Bundy, president of the Larson Research Center, where we are unveiling the universe of motion. Today is January 1st, 2016, and I hope everyone had a joyous and safe holiday season. On this initial webcast, we want to discuss more on the coming revolution of the fundamental physics. This was the title of a series of lectures that I gave back in 2008 in Clearfield, Utah, that was based on lectures from Dr. David Gross, a presentation he gave the year before, and which is now available on our YouTube channel here on our LRC Physics channel. You can, it's brand new, you can go there. There are several things. We'll refer to a couple more as we go along, but hopefully you'll be able to go there and like the channel or subscribe to it and like it on our Facebook page or our group of the same name, LRC Physics. And we're also on Google Plus, of course. Well, I had intended to present a much longer series of lectures than I ended up doing in 2008, but personal circumstances prevented it. I had indicated at the end of lecture 2, you can see the 2 playlists for the 2 lectures on the LRC Physics channel, that the next lecture would be on the unification of mathematics. Now, about 9 years later, I would like to present that next lecture. However, this time, technology makes it possible to do it online using Google Plus Hangouts on Air, which is much, much easier to do than a live presentation before a live audience. The new online lectures are live at the time they are given, and we can have an audience. We can accommodate up to 5 or up to 9, I guess, including the host. It's 10 altogether participants on the show that constitute a live audience, but also then, of course, an unlimited number of non-participants can watch live. So happily, Google automatically records the website for later viewing on our Google Plus page and on our YouTube channel, which is, of course, a terrific logistical bonus for us. Well, of course, a lot has happened in the intervening 9 years since that last lecture, as far as developments in the LRC's RST-based physical theory. But even back then, we understood the importance of unifying the RST with mathematics. Larson always deflected criticism of his work that complained of a lack of a mathematical formulation of it, contending that it didn't require a new mathematical formulation, but that the mathematics of legacy physics was sufficient for the new system if only it was correctly interpreted. It's the inventive concepts that are wrong, not the mathematics he maintained. However, we at the LRC disagree with this conclusion and have sought to find the proper mathematical formulation for our RST-based theory from the very beginning. It's been quite a ride, actually, and it will take a book to explain it all, but in a word, not even the legacy system of physical theory is unified with legacy mathematics. Therefore, if we are to unify the RST-based theory with mathematics, we must recognize then that the challenge hasn't even been met by the scientists of the legacy system, implying that much new ground has to be broken, and clearly this is not going to be easily accomplished. Peter Woit gave a talk at the University of Central Florida entitled "The Challenge of Unifying Particle Physics," which I referred to at the end of lecture 2 on the coming revolution of fundamental physics. He really does a good job of explaining what the standard model of particle physics is. And then in the last slide, he makes the point, which is the most interesting of all, The challenge of unifying particle physics, he insists, is really the challenge of unifying the mathematics of the Standard Model. Specifically, he makes three important observations. Number one, the mathematics of the Standard Model is poorly understood in many ways. The representation, number two, the representation theory of gauge groups is not understood. And number three, the unification of physics may require the unification of mathematics. But in the midst of these three, he puts another bullet that states, quote, one indication of the problem with string theory is it is not formulated in terms of a fundamental symmetry principle. What is the group? Close quote. Well, in other words, the trouble with the Standard Model is that it works very well, but we don't know why. And the trouble with the string theory is that it doesn't work very well, and this may be because it doesn't work the way the Standard Model works. The answer to the question, what is the group, is, of course, that there isn't a group that corresponds to the vibrations of a string, even though there are two ends of the string, one positive and the other negative, which is the basic form of a group according to Voigt. Thus, it seems that theoretical physics is caught on the horns of a mathematical dilemma. On contemplating this observation, it's only natural to ask what the new mathematics, the reciprocal system of mathematics, or the RSM as we're calling it, has to say, if anything, about this predicament. If you go to our website, you can see we've been writing about this reciprocal system of mathematics that we're trying to put together for some time. You can find it there on our website, lrcphysics.com. So just go there and click on the, you can do a search. There's a search button there. And also you can go to the New Math blog and find the entries for the reciprocal system of mathematics recorded there. Well, there are a great many aspects to it, and the problem that is the most difficult challenge for us in answering it is the decision of where to begin. After contemplating it for some time, though, I think the best thing to do is to just start over at the very beginning with the so-called fixed coordinate system of 3 dimensions. After all, the fixed 3D coordinate system is our basic framework of numbers and magnitudes. Indeed, it's the framework upon which we have built our modern technology. Like women in a worldwide sewing circle, constructing various quilts by means of quilting frames, mathematicians and physicists worldwide have worked together to sew the intricate patterns of modern physical concepts into frames of the 3D fixed reference system. Interestingly enough, though, is the fact that for the scientists with their functions and variables, as well as for the ladies with their needles and threads, the most important and central principle of their work is the principle of symmetry. So here is Peter Woit, a passionate member of the inner circle of theorists, standing up at the edge of the frame, so to speak, to complain about the lack of clear symmetry principles in the latest work of the group. I don't get it, we can almost hear him saying. This new pattern sucks. We can imagine him walking around the frame, pointing out how the intricate needlework, gorgeous and elaborate as it is, in places, is just not driven by a symmetrical approach overall, as a whole. But we can imagine someone like David Gross protesting, the overall symmetry doesn't matter because you can't see the darn thing as a whole anyway. The only thing that really matters is the local symmetry, which everyone must admit is breathtaking. Well, of course, Peter and all those who agree with him are not convinced at all by this argument. Yet, what can they do? To go back now and start over is unthinkable, but at the same time to find a principle which would serve to unify all the independent patterns into one symmetrical pattern seems impossible at least at this advanced stage of the work. Nevertheless, it's not the case for amateur but honest investigators like Larson. As he so eloquently pointed out, the amateur investigator has no vested interest in the current fabric of mainstream theory, and he is free to start from the beginning. Certainly, Larson's not the only one to recognize this. In fact, so many amateurs have tried their hand at coming up with their own alternative that their ranks have become legion, but they are usually summarily and derisively dismissed by the professional craftsman as naive, with hopeless lack of proficiency in the essential skills to work on the elaborate quilt. And Larson, of course, is no exception to this classification of so-called cranks. Nevertheless, and notwithstanding the lack of interest of the professionals and amateur suggestions, Larson's approach should not be lightly dismissed, which I would invite my guests to discuss at this point if we had any, but no one has been able to connect with us, so we'll just have to go on in a lecture type form. I wanted the format to be more, to be less formal, and so that we could get into an actual discussion of these things, but it's been a little bit difficult, I guess, to get people to join in, at least at this point. Hopefully in the future we'll be able to get more people involved. But Larson's approach should not be lightly dismissed, if for no other reason than because his suggestion is completely and totally different than all the others. In effect, he suggests that the sought-for global symmetry, which can accommodate the desired local symmetry, can indeed be found, but only if we modify the fixed 3D reference frame first. Since historically modifying this frame itself in appropriate ways has always led to the greatest advances in physical theory, this alone ought to get the attention of the pros. Unfortunately, however, Larson never clearly understood how his modification of the frame worked mathematically. Indeed, he always insisted that his new non-fixed frame of reference was consonant with existing mathematics. But as we have discovered since, here at the LRC, this is far from the case. The truth is, his new non-fixed 3D frame of reference constitutes a revolutionary new approach to mathematics of the reference frame, the mathematics of the reference frame, which completely transcends the transformations of the past. The fundamental reason that this is so is that Larson's recognition of the reciprocity of space and time, wherein he defines space and time as nothing more or less than the reciprocal aspects of motion, of changing magnitudes in the equation of motion, applies equally well to rational numbers in general. What we call scalar quantities or zero-dimensional numbers are best understood as reciprocal aspects of positive and negative magnitudes. In other words, the observed properties of physical magnitudes, quantity, duality, and dimension, are also the properties of abstract numbers. When these are understood as the ancients understood them, as two reciprocal aspects of magnitude, the whole world changes. With this exceedingly simple change in our most fundamental abstract concept, so obvious yet so revolutionary, we can actually construct a new, totally different, non-fixed 3D frame of reference that Larson called a natural frame of reference, upon which to build beautifully symmetric patterns of physical theory that contain all the local fixed frame variations that enchant us so, and to do so, we can do so without sacrificing the overall symmetry of the quilt, so to speak. Well, that's a mouthful. The key to understanding how all of this works is found in understanding what we call the operational interpretation of the rational number, where the defining operation is the reciprocal relation of rational numbers just described. Given the OI number, operational interpreted number, we can form both negative and positive numbers and zero of more than one dimension without the use of imaginary numbers. One of the most important things that this then does for us is to give us a better handle on the abstraction of infinity and infinitude, which promises to help us to eventually extricate ourselves from the horns of the continuous slash discrete dilemma, which has so exasperated modern man's difficulties in constructing consistent physical theory. A good overview of the history of this drama is given in the playlist of videos named, quote, Important Outside Presentations, unquote, which is found on our YouTube channel. So you can go there and watch these videos. There's not a whole lot of them. There are 3 of them. And the first one is this lecture by David Gross entitled The Coming Revolution in Theoretical Physics. The second is the lecture by Lee Smolin entitled Physics in Trouble, Why the Public Should Care. And the third is by Joe Polchinski entitled Gravity and Quantum Mechanics, The Quest for Unification. Well, these prominent scientists giving these lectures are all theoretical physicists. 2 of them are prize-winning theorists. And the picture of what we now call the legacy system of theoretical physics, or the LST, which emerges from these lectures, is not very pretty. I think it clearly shows that the quest for the unification of quantum mechanical theory and the space-time gravitational theory of Einstein has uncovered more than the lack of understanding the very fast, the very small, and the very massive. But as David Gross stresses, and this is a quote of his that I took from an NPR interview a few years back, where he says, a lot of us are waiting for such a new idea that will give us an alternative to our traditional notion of space and time, perhaps, or perhaps some other new idea. Something is missing, though, something that is most likely not just another technical development, another improvement here or there, but something that truly breaks with the past. And all the indications are that it has to do with the nature of space and time. Well, here at the LRC, we believe that we know exactly what that new idea is, which Gross identifies as an alternate to our traditional notion of space and time that truly breaks with the past. The new understanding of the nature of space and time is that they are 2 reciprocal aspects of the same thing, motion. Distance is not a space or a time magnitude, but a space and a time magnitude or a motion, which you can prove because you can't measure it without motion. You can't measure space without moving something or without observing something that is moving. It might be a yardstick that you have to move in between 2 different points, or it may be a laser that has to move, a laser light, that beam that has to move between 2 points, or a sound wave that has to move between 2 points, or some other way. But you have to use both space and time in order to measure either one. And it's just not possible then to say that there is space or that there is time outside this relationship of space and time, the only known relationship of which is motion. So this idea then that the various positions in what we call space that are distant from one another are just a history of the motion it took to move them there. This simple but revolutionary new idea is the foundation of a whole new system of physical theory called the Reciprocal System of Physical Theory, or the RST, which is the work of Dewey B. Larson, the late Dewey B. Larson. The full name of the Larson Research Center, or the LRC, is the Dewey B. Larson Memorial Research Center. It was established as an institute of studies in theoretical physics based on Mr. Larson's reciprocal system of physical theory. The theoretical investigations of the LRC investigate the consequences of the assumption that the universe is not a container of matter framed by 3D space, evolving over time as is necessary in the theory of quantum mechanics, nor that it consists of a 4D space-time continuum interacting with matter as posited in the theory of general relativity. The new assumption is that everything, including matter, energy, and even space-time itself, consists of nothing but discrete units of a newly identified motion called scalar motion. With its two reciprocal aspects of space and time related in the familiar equation of motion, v equals ds over dt. In other words, velocity is equal to the change in space over change in time. Discrete units of this theoretical motion and combination of these units, various combinations of these units combine to form photons of varying frequencies, which then propagate outward from matter as radiation and form combinations of subatomic and atomic entities of matter and antimatter with different spin, charge, and magnetic properties, which gravitate as entities of matter but are convertible into energy according to the established principles of symmetry and laws of conservation. However, unlike in the case of the familiar motion of everyday objects, or what we call vectorial motion, in this case, the discrete units of scalar motion do not require a change in the location of an object to define motion as distance over time, but rather it is assumed that the space aspect of this motion increases naturally, inexorably, just as its time aspect does. It assumes that a continuous march of space exists, measurable by a space clock, which in conjunction with the continuous march of time measurable by a time clock defines a universal motion or space and time progression. The continuous ticking, if you will, of these two clocks constitutes the initial condition of the theoretical universe of motion. Well, that was in the time when Larson invented it. But of course, since then, it was discovered that we can observe the expansion of space and time. This progression is universal. We see that space is literally increasing as time increases. And we'll get into that in our future lectures. We covered a little bit of it in the past lectures. If you want to go back and watch those, as I said, that are on our YouTube channel. Well, what this means then is that the new system is a system of scalar magnitudes, not a system of vector magnitudes as we are used to. In physics, in the legacy system of physics, in our modern physics, vectors are directed magnitudes while scalars are not directed magnitudes. That is, scalar magnitudes do not have a single direction that can be defined in terms of 3 dimensions in a fixed reference system. Consequently, in a 3-dimensional physical system, scalar magnitudes of motion are magnitudes of motion in all 3 dimensions simultaneously, or magnitudes of volume only as viewed in a 3D fixed coordinate system. Since the entire field of theoretical physics has only dealt with vector magnitudes of motion from Newton's day to this, a change in the system of physical theory from a vector-based system of motion to a scalar-based system of motion constitutes a significant new direction in the traditional program of theoretical research originally established by Sir Isaac Newton. To make this important distinction in the work of the LRC, we refer to the vector-based system as the legacy system of physical theory, or the LST, legacy system of physical theory. Now, in mathematics, there are exactly 4 norm division algebras: the real numbers, the complex numbers, the quaternions, and octonions corresponding to the four elements of geometry, the point, the line, the area, and the volume, as the dimension n of the numbers in these four-dimensional systems is increased from 0 to 3. Unfortunately, however, the algebras of these systems lose their distributive, commutative, and associative properties one by one as n increases, as the dimensions increase, until for n equals 3 dimensions, none of these important algebraic properties remain. We suspect that the reason for this is the use of the ad hoc invention of imaginary numbers in the definitions of these four number systems. Imaginary number-based numbers like vector magnitudes have direction, but scalar numbers like scalar magnitudes do not have direction. They have a duality, however, that we call direction with quotes instead of simply they have that quote direction rather than the direction that we're normally used to. And it's simply defined in terms of less than and greater than a unit ratio. So this is very important. Where we have 1 over 1, we can have 1 over 2, which is less than 1, and we can have 2 over 1, which is 1 unit both above and below the unit. And we've arbitrarily, they're one's the inverse of the other, and we can talk about them in terms of fractions, but in reality, there are two different directions of the magnitudes inherent in nature. Well, anyway, we'll get more into that in our upcoming lectures, but we don't want to deal with the details of it tonight. But the consequence of all this is that the physics of scalar motion cannot use the multidimensional mathematics of vectors and spinors, but must use the multidimensional mathematics of scalars, which is a new concept in mathematics. And since the entire field of algebra and geometry has only dealt with imaginary number-based systems from Hamilton's day to this, a change in the number system of modern mathematics from multidimensional imaginary number-based systems to multidimensional scalar number-based system constitutes a significant new direction relative to the traditional program of mathematics originally established by Hamilton, Heaviside, Gibbs, and others. To make this important distinction in the work of the LRC, we refer to the multidimensional imaginary number-based system as the legacy system of mathematics, or the LSM. So we've got the LST for the legacy system of physical theory, and we have the LSM to refer to the legacy system of mathematics. But the point is they both use vectors. They're all based on vectors. Their algebra is based on imaginary numbers to obtain vectors in various dimensions. But now, one of the strongest arguments that Larson proffered was actually a philosophical argument. He made a case against what he called inventive science in favor of inductive science, which is based on the facts of observation. Unfortunately, throughout history, new observations have upset the inventive science of man. And of course, the most instructive case of this is still extant, and it's that of the Greeks, whose invention of epicycles to explain the motion of the planets is the most clear example of all this. However, while Larson's case against inventive science is one that ought to be taught in universities, it seems to still be the mode of the day, unfortunately, with major figures in science such as Einstein openly admitting their recourse to it unabashedly. Today, inventive science is building upon inventive science, and the results are the current controversies articulated by Lee Smolin and Peter Woit in their protests against string theory, which caused such a stir a few years ago when their books, The Trouble with Physics and Not Even Wrong, first came out. Nevertheless, the inventions, though well-meaning, continue unabated. Let's watch a clip from Joe Polchinski, his video that I posted on our YouTube channel, which I mentioned earlier. to see what we're talking about.
So each of these three extremes, very fast, very massive, and very small, is the arena for one of the great theories of physics: special relativity, general relativity, and quantum mechanics. These were the three revolutions in physics from the last century. And each of these theories is now tested very, very well. And these three theories provide for us still the basic framework for our understanding of space and time and matter, and even in quantum mechanics reality. Of course, these are all about 100 years old, you'll notice, long time. But the good news for those of us who are still working in the field and want to do something interesting is that these revolutions aren't complete. We know that. Because if you think about it, discovering these three new theories really opens up three new questions. We've understood the very fast, the very massive, and the very small. But for example, what if an object is both very fast and very small? What if we have to deal at the same time with both the strangeness of special relativity and the strangeness of quantum mechanics? And that's a very good question. That's a very deep question. And the first person to address it was Paul Dirac. So that was a very fruitful question. But that wasn't really that wasn't the end of the story. This problem of unifying special relativity and quantum mechanics went on after Dirac. It actually required that we develop a sort of a whole new mathematical language, quantum field theory. And this unification was also the key to formulating the Standard Model, which is the name given to our basic theory of matter. The Standard Model was formulated around 40 years ago, and just as Dirac predicted a new particle, the Standard Model predicted, well, depending on when you start counting, 5 new particles, and one by one they've been discovered. The gluon, then the W and Z bosons, then the top quark, and just this past year, the Higgs boson. Now, putting together the Standard Model was a bit more involved than what Dirac had to do. Dirac really just had to do what I described on that one slide. To understand the Standard Model, it required additional experimental data. It required additional theoretical ideas. But really, the fact that this theory had to incorporate both special relativity and the quantum principle was a very strong constraint on what it could be. It really is it's the reason why one could find this theory with such precision and predict 5 particles, predict their detailed properties, and get it right. So this is a fantastic example both of humans' ability to figure things out, and also their ability to go and, in the end, do the experiments, because these were heroic experiments to discover these particles. And it's worth mentioning that physicists at UCSB played major roles both in the theory side and in many of these discoveries. So, the problem of the very fast and the very small together has been a very fruitful one. But there's 2 more pairs to consider. What if an object is both very fast and very massive? And that turns out to be an easy one, because when Einstein first wrote down general relativity, special relativity was built in, so he answered that all at once. The interesting pair, the one that we're still, the one that this talk is about, the one that we're still so puzzled by today, is what happens if an object is both very small and very massive, or all 3, small, massive, and fast. And this is the problem of quantum gravity. Quantum for small, gravity for massive. Now, you might ask, isn't this a contradiction? Can something be both very small and very massive? And so I'll mention some places where this can happen. First of all, it can happen in particle collisions at extremely high energies. So particle physicists like to bang particles together, and I'll be saying more about this later on. But if you collide them hard enough, you will get into this regime where, again, you have both the very small and the very massive. A second place where this comes up, so the universe we know is expanding. But if we follow it back in time, it was becoming smaller and denser. And in fact, observationally, one can follow this back remarkably far to a time when the universe was vastly smaller and vastly more dense than it is today. Very close to this regime of quantum gravity where both quantum mechanics and general relativity, the small and the massive, are acting at the same time. And as more precise observations come up, we get closer and closer to that regime. So understanding the unification of our theories of the small and the massive is also a key to understanding how the Big Bang began. And finally, there are those black holes that I mentioned, and if you follow the black hole to its final fate, it ends up, as far as any theory we have now, crunched down to a point. And so you have there something which is truly massive and small. And so here are three places where you have to worry about both of those theories at once. Now, all of these experiments or regimes are very far, all of these things I've described are really very far from direct experiment. Maybe it's getting closer with the early universe, but they're still really very far from direct experiment. And so to do what we want to do, we have to rely heavily on theoretical reasoning the way Dirac did. Now, I described what Dirac did, and what it sounded like and what it basically was, it sounded like he sat around fiddling with equations. And you might imagine that that's what a theoretical physicist does all day, sit around and fiddling with equations. And it's sort of true, but Dirac was an especially pure physicist in many ways. He was very mathematical, and there were other kinds of reasoning that are very useful. And I want to talk about a particular kind of reasoning which is extremely valuable, known as a thought experiment, which has been employed by many people. And to illustrate what this is and how it works, I want to tell you about my favorite thought experiment, which is the one that James Clerk Maxwell used to figure out the laws of electromagnetism. So here are more equations, but it's okay because they're on a t-shirt. And these are the equations when Maxwell was done. But when he started, he had something less than this. So I've covered up, you'll see one term and the bit about the light. So this is the equations as they came to him. And these equations were discovered by and large in experiments. In fact, they each have a name. These terms on the right each have a name. This says that these are the equations that describe the behavior of electric and magnetic fields. So this term says that electric charges make electric fields in a certain way. And this term says that electric currents make magnetic fields. And this term says that there's another way to make electric fields, which is if you have a magnetic field and it's oscillating or changing in time. And again, these are all found experimentally. They agree with the data. But there's something wrong with these equations as they stand. They actually don't make sense if you push them far enough. And so Maxwell exposed this with a simple thought experiment. Here's the thought experiment. It's a simple circuit. So you've got a battery, and a wire, and a switch. And then you have a break in the wire and a couple of plates, capacitor plates. So you have a break in the wire with a couple of metal plates at the break. And the experiment is, first of all, just to close the switch. And when you close the switch, the battery starts pushing on the charges and the current starts to flow. And at the gap here, they can't cross over, and so they pile up for a little while at those plates. Okay, so the experiment is first to close the switch, and then to measure the magnetic field at that X there. And the problem is, if you do that and you try to use the equations that were there before Maxwell, you don't get a sensible answer. You can solve them in two different ways, and get two different answers for the magnetic field. So there is something wrong with those equations. This thought experiment exposes it, and with a little bit of trial and error, and actually more than that, with a certain amount of sort of modeling and guesswork, Maxwell figured out that he could fix them by adding in one more piece. And now these equations are all perfectly consistent. And he got, as Dirac did, an unexpected bonus. Because he set out to explain the laws of electricity and magnetism. And there's this law that says a magnetic field can produce an electric field. And there's this new law of his, which says that an electric field can produce a magnetic field. And so now you get one producing the other. You get not a chain reaction, but you get an endless wave, in fact, of electric and magnetic fields. And when you solve these equations, you find that wave moves at the speed of light. And suddenly he realized that he understood the nature of light, which he hadn't set out to do at all. It just popped out of his understanding of electricity and magnetism. Not only light, but this also predicts the entire electromagnetic spectrum, which was at that time unsuspected, from radio waves on up to X-rays and gamma rays. So when I heard about this, when I learned about this, I thought this was pretty much the greatest thing ever to understand the nature of light by this kind of reasoning. And I said, that's what I want to do. And I still feel that way. Now, you might ask, why was this a thought experiment? Why wasn't this a real experiment? Well, there's a good reason. Because in order to actually measure that term, you would have to actually open and close the switch very fast. You would have to open and close the switch in about a billionth of a second, a nanosecond. And you can imagine that was rather hard to do. And so this was not discovered experimentally. It was discovered by the kind of reasoning I described. 25 years later, Heinrich Hertz figured out how to open and close a switch on a nanosecond time scale and confirmed Maxwell's equations. Okay, so that's the nanosecond time scale. Now, to probe quantum gravity, to probe it directly, one has to get to the nanosecond time scale. Now, how do we know that? Well, we know that as follows. I told you there are these three theories, these three revolutions, and each of these revolutions comes with its own constant of nature. So when I say special relativity sets in when things move very fast, you can ask how fast? Well, close to the speed of light. So C here is our notation for the speed of light. That's one of the basic constants. For quantum mechanics, it operates when things are small. How small? Planck's constant tells you how small. And finally, gravity, very massive. How massive? Newton's constant. The gravitational constant tells you how massive. So each of those three theories comes with a constant of nature. And now, it turns out, if you want to construct a time, if you want to construct something, if you want something which is measured in seconds, there's a unique way to combine these three constants. Here it is, kind of funny looking, but that's what it is. There's a unique way to combine these three constants to get something that you would measure in seconds. And when you do that, the number of seconds, the scale of this theory is again a nano to the fifth second. So this is the kind of reasoning that tells us that just as that we needed nanoseconds to test Maxwell's equations, we need 5 nanos to get to quantum gravity. Now that's 2 nanos too many. The LHC can get to roughly a nanosecond. So our most powerful particle accelerator, which has been operating in Geneva for the last few years, probes physics at roughly a nanosecond. So much better than Hertz, but still well short of what we need for quantum gravity. And so Once again, we're going to have to rely on thought experiments. And there's a reason why this might be a profitable way to proceed. And to explain this, let me go back to Maxwell and think about why he was able to succeed. Why was he able to complete these equations without experimental data, but just by theoretical reasoning? Well, it was really because the experimentalists had already did most of the work. They'd found 3 of the terms. He just had to figure out the 4th one. Actually, it's a little bit harder than I made it look here, because the way I've written these equations is the way we write them today. 150 years ago, there was much less sense of how to think about these things. The equations were written in much longer and messier forms, and it was really much less obvious what their content was. So it wasn't quite as simple as just writing that. But really, the way you see, thought experiments are very useful if you have most of the picture and you're just trying to fit in the last few puzzle pieces. They help you figure out. This is one of the times they're useful in other ways as well, as I'll talk about. But one of the ways they're useful is if you already know a lot and you're trying to fit the things that you know together. And in some ways, that's where we are in quantum gravity. We have quantum mechanics. It's a very well-tested theory. We have general relativity, another very well-tested theory. And so using thought experiments, I told you about these extreme regimes where quantum mechanics and gravity both operate at the same time. By thinking about what happens in these regimes, we can, as with Maxwell, figure out where the 2 theories don't fit together.
Well, he goes on to show how their thought experiments, as he calls them, on black holes have brought the conflict of quantum mechanics and general relativity to a head, but in terms only the most dedicated specialists can understand. It is results from these thought experiments that David Gross now tells us that space and time, as they are now understood, are doomed. Well, it's interesting to see how they think, and as he said, they're trying to figure things out, but they don't realize that they're inventing things, and they think they're on solid ground, but they don't understand this issue very clearly, that they're working from things because they think they've proved them. Just like in the days of epicycles, it was proven by the results that their thinking was correct. But of course, the concept was totally without merit. But they didn't know that until the knowledge that made it clear came forth. But so the fact is that now, without a knowledge of a few important observations, these modern scientists just keep getting wound tighter and tighter around the theoretical axle. They don't know that space is the reciprocal of time, that the properties of one are the properties of the other, and that they have no meaning apart from their nature as 2 different aspects of the same thing. The modern theorists have no idea that the concept of force as an autonomous, independent entity does not exist, that it's simply a quantity of acceleration that has been defined by Newton. They have no idea that scalar motion is an observation, not an invention, and that it deserves to be studied and investigated apart from the vector motion of inventive science. They don't have any idea of any of these things, and so their thinking is not inductive in that sense, based on the latest observations, but it's based on their concepts, invented concepts like space-time. That's an invented concept, and then they go on to see it being warped by gravity, intense, massive gravitational objects. And so then the black hole, so-called inventive science, an invention of an invention, develops, and then you have the singularity at the bottom, and so they use their mathematics to study these things. You can watch the entire video and see what I'm talking about. But eventually, you know how he drew that picture of the black hole funnel coming to a point at the end. Well, eventually it gets clipped off near the top, and space disappears. And that's why David Gross is saying that space is emergent, and therefore, and if space is emergent, time must be emergent, and therefore they both are doomed. Well, those both concepts are doomed. I think the concept that is actually doomed are the invented concepts. But the thing is, Larson's talk on the dangers of inventive science is available on our LRC Physics YouTube channel and well worth watching. But the point I want to stress tonight is that Sir Rowan Hamilton, the father of vector algebra and quaternions in the mid-1800s, recognized the same thing in mathematics. Said he, quote, "For it has not fared with the principles of algebra as with the principles of geometry. No candid and intelligent person can doubt the truth of the chief properties of parallel lines as set forth by Euclid in his Elements 2,000 years ago, though he may well desire to see them treated in a clearer and better method. The doctrine involves no obscurity nor confusion of thought and leaves in the mind no reasonable ground for doubt, although ingenuity may usefully be exercised in improving the plan of the argument. But it requires no peculiar skepticism to doubt or even to disbelieve the doctrine of negatives and imaginaries when set forth as it has commonly been with principles like these: that a greater magnitude may be subtracted from a less, and that the remainder is less than nothing. That two negative numbers, or numbers denoting magnitudes each less than nothing, may be multiplied the one by the other, and that the product will be a positive number, or a number denoting a magnitude greater than nothing. And that although the square of a number, or the product obtained by multiplying that number by itself, is therefore always positive, whether the number be positive or negative, yet that numbers called imaginary can be found or conceived or determined and operated on by all the rules of positive and negative numbers, as if they were subject to those rules, although they have negative squares, and must therefore be supposed to be themselves neither positive nor negative, nor yet null numbers, so that the magnitudes which they are supposed to denote can neither be greater than nothing, nor less than nothing, nor even equal to nothing. It must be hard to found a science on such grounds as these, though the forms of logic may build up from them a symmetrical system of expressions, and a practical art may be learned of rightly applying useful rules which seem to depend upon them, yet that's the problem." Well, close quote. In other words, Hamilton was complaining that algebra was an inventive science, not an inductive one. I wish Larson could have read this. Maybe he did, I don't know, and have understood that what he observed about inventive science and its effects in the physical sciences, Hamilton had likewise seen in the mathematics of algebra. In the next lecture, that was scheduled now for next week at the same time on the Honest Investigators Talk Shop program, I will be presenting the beginning of a new inductive approach to mathematics, which is, in reality, a new approach to the unification of the algebra of mathematics to go along with our new approach to theoretical physics. And it is thus a return to inductive science in both cases. Well, so that's it. And till next week, this same time, 7 p.m. on Saturday evening, we will say goodbye. Till then, thanks.